Hi everyone. In the last lecture we talked a little bit about, the way in which quantum mechanics provides a foundation for the periodic chart and the ionic bond. Here we can also talk about how quantum mechanics provides some insight into the covalent bond. So, for example, let's imagine we have two hydrogen atoms separated by a large distance in space. And their ionization energies are going to be 13.6 electron volts, just like they are normally. Now, that's what these two pictures represent. Now, as I bring the hydrogen atoms closer together, their electron orbitals start to overlap. Okay, they start to touch. I mean, really, they're always touching, but they start to overlap in a significant way. And those, remember, the electron orbitals are really waves. They're vibrating, right? They're ringing, in a sense. And so what happens is those two orbitals come together and they start to interfere in the same way that we've talked about wave interference already. It's kind of the same phenomenon. And so what happens is that those orbitals actually create one kind of larger pattern, and that pattern either constructively interferes or destructively interferes. And so in this case, for example, if the orbitals are aligned in such a way, we've got a constructive interference here. Here we've got destructive interference, okay? The two orbitals. And so as we bring the two orbitals together, we start to get a separation in energy level where the constructive interference actually becomes energetically favorable, because it's kind of resonating with itself. The destructive pattern gets worse and worse the closer and closer they get. That's always the case. And then as we get extremely close, the Pauli exclusion principle starts to kick in again. So what we have here is a trough. Now this trough indicates a point of equilibrium. That is the covalent bond. So as we bring these two atoms together, the vibration of the electron orbitals constructively interfere and create a situation that is energetically more favorable than if they are apart. And that is precisely what we need to have a covalent bond. Now this gap here, which for a hydrogen bond is 4.5 electron volts, that gap is called the exchange energy, for a reason related to the indistinguishability. You can swap the electrons. That's where the word exchange comes from. It's not really important to understand. The point is that there's a certain energy level that's associated with the fact that we bring these two together. It's basically the level of the covalent bond. And that's kind of all there is to it. So, we can talk about, that was a very simple case, but all sorts of orbitals, once they start to overlap, they have this effect where the two orbitals combine together into two combinations that are either energetically favorable or not. They split. The net orbitals split into two. And because the two electrons can follow one another with opposite spins into this favorable orbital, they do so. And so you've got two electrons in this, and basically we say that the atoms are sharing those electrons. Now, one other aspect of this exchange energy is it actually explains ferromagnetism. Remember I mentioned that ferromagnetism is fundamentally a quantum mechanical effect? This is what happens. In a sense, you could say that the magnetic moments are covalently bonded together to line up. And when they do that, you've got this accumulation in a ferromagnetic material. And basically, this exchange energy explains why certain materials have a certain energetically favorable state, which lines up all their atomic magnetic moments.